All right, number 41. This problem has to do with the photoelectric effect. And the general formula for the photoelectric effect is the energy of the... the general formula would be the energy of the incoming photon. Well, part of it goes towards the work function of the metal. And then any energy that's left over goes to the kinetic energy of the emitted electron. So this is the maximum kinetic energy of the emitted electron. So I had that in mind when I wrote down this. The energy of the photon is h nu. So we want to write this in terms of frequency versus stopping potential. So frequency of the incoming light versus the stopping potential is not related to the work function, but it's actually related to the kinetic energy of the electron. And energy, if you remember in E&M, energy is charge times voltage. So stopping voltage is related to the frequency like this. And the stopping voltage is the dependent variable, so I think I solved for the stopping potential here. Notice how, so not only, I moved this over to the other side to solve for stopping potential. Really, we know something about the slope of this line. So notice how, sort of what I did in going from here to here is I took the differential of both sides, sort of finite differential, and that gets rid of this work function right here. So I just said for every change in frequency, there's a corresponding change in stopping potential, and that gets rid of the work function, which has to do with one of these intercepts. So they're asking the slope of the line, which is delta V over delta nu. So delta V over delta nu looks like that's H over E. So you can kind of see right away from this formula. So we have an oscilloscope screen. And we have two waves that aren't quite in phase with each other. So notice what I did here. I saw by how much one of the waves was out of phase with the other wave. And I didn't write it in terms of anything except for number of squares. Okay, so to get channel 2, you have to take channel 1, and you can move it 2 squares over to the right. So 2 squares doesn't really mean much by itself, but we can see that one whole wave corresponds to 1, 2, 3, 4, 5, 6 squares. So if we need to move this wave over 2 squares, and moving it over 6 squares would be a whole wave, or 2 pi radians, 360 degrees. Moving it 2 squares is a third of the way, or a third of the phase, 120 degrees. Now, I would have to give it a little bit more thought if one of the answer choices was 240 degrees, then I have to figure out, well, moving it to the left or moving it to the right, but there's none of that work required. There's no 240 degree answer choice, so yeah, it's able to move on at that point. 43, I got wrong. My chemistry teacher would be ashamed. So when I read this, I thought, I don't know why, but when I read this question, instead of diamond, I thought of graphene. And I was thinking, oh, nice 2D sheets. They look like hexagons. And I just kind of immediately chose hexagons. But no, in the diamond structure, that's not the 2D sheets. It's all the carbons are single bonds, and they take on tetrahedral form, sp3 hybridization. So they are just tetrahedrons. I was acting too much like a physicist and not enough like a chemist on that one. But yeah, tetrahedron. Number 44. BCS theory, Cooper pairs, superconductors, you should be thinking condensed matter physics. And so that's why when I read A and B, I just immediately crossed it out. I said, you know what, that has nothing to do with condensed matter. And then in the other answer choices, I know a little bit about, so the Casimir effect has something to do with vacuum polarization. So you can see why I wrote, aren't these similar? And also that has to do with vacuum, not much matter, whereas this is condensed matter. So, I took an educated guess and said probably doesn't have anything to do with C and E. It's probably going to be D. And it just seemed to make sense with condensed matter physics. I'm not a condensed matter physicist, so I sort of guessed on that one, but yeah. I should know what it is, though. Okay, 45 has to do with Doppler effect in sound, not for light. And so the formula to have in mind is so it's the velocity of sound plus or minus the velocity of the receiver over the velocity plus or minus the velocity of the source. So this times the emitted frequency will give you the heard frequency. Now, in this problem, instead of the source or the receiver moving, it's actually the wind that's moving. So really, these v's are the speed of the receiver and source relative to the air, relative to the it's assuming that the air is fixed. If the air is moving, then what you have to do is you have to find the relative motion of the source relative to the wind. So if the wind is blowing from the siren towards the person, in the frame of the wind, the siren is moving away from the person, or the siren is moving, with some speed, this speed away from the person. And so the source, and so if the source is moving away, that's a perceived frequency that would be lower, and so that made me choose the plus right here. Right, it's a plus, the denominator gets lower, the heard frequency gets lower because of the source moving away. But then, in addition to that, the receiver is moving, in the wind's point of view, in the wind's reference frame, the receiver is moving towards the siren, and so that tends to increase the frequency, so I chose a plus right here. But it's the same amount, and so the same speed of sound waves in air, and then same speed right here. Looks like the ratio is 1, so the heard frequency is the same as the emitted frequency. So we still have C, 1200 hertz. Okay, 46. We have sound waves, and we want a disappearance due to a single opening. So you should think of diffraction, diffraction for sound waves rather than light. So when I'm thinking about diffraction, the equation that immediately comes to mind is A sine theta equals n lambda, counting these are the diffraction minima, where n is a non-zero integer. And we want the first disappearance, so we plugged in n equals 1 right there. We're given that theta is 45 degrees, and we're given the slit width, it's 0.14 meters. So then you can solve for lambda, but we actually want frequency, so at b over f, and then solving for f. And notice how I didn't plug in numbers too early here, and it's a good thing because here I have a square root of 2, which is about 1.4. And the a, this is probably not a coincidence that the slit width is 0.14. So that's a nice just factor of 10 right there. And so really, we don't have a calculator, but it's really not so bad. They know you don't have a calculator. They're choosing the numbers to help you out with this sort of thing. So don't be too freaked out by any calculations. Just save the number plugging in until the end. Yeah. 47. This has to do with harmonics, standing waves for a pipe. And by telling us that the pipe is closed at one end and open at the other, says that there's a node at the closed end and an antinode at this end. So the first thing I drew was this pipe, open at one end, closed at the other. I drew the node right there. And then the game is to, you can draw waves that fit in here so that you have an antinode right there. So the largest wavelength that fits in there it'll be quarter of the wavelength is equal to the length of the pipe. That's the fundamental. And then the next higher harmonic will be, well, instead of a quarter, it looks like I can fit that much in there. It'll go up and then come back down right here. So I wrote an equation for these two. So here, the length of the pipe is a quarter of the wavelength. And then the other one, it looks like I'm fitting 3/4 of the wavelength. So 1/4, 2/4, 3/4, but I didn't quite go back to make a full wavelength. So 3/4 of the wavelength is the length of the pipe. So that gives me this equation. And we want the, so if I take the ratio of these two equations, if I take one and divide it by the other, I get 1, well, looks like I get 3 lambda next highest frequency is equal to lambda naught. So if the wavelength decreases by a factor of 3, the frequency goes up by a factor of 3. So I take this frequency of the fundamental, multiply it by 3, and I get D. Number 48. This has to do with logic gates. I happen to know that this means and this means or. I suppose even if you didn't know that, you would see that, well, the combination of quantities to get E is the same operation that you're doing to C and D right here. So it looks like C and D all has the dot, so that rules out the plus right here. So probably dot for whatever this symbol is. But it's an and. So you know, if you have a 1 and a 0 right here, 1 and 0 gives you nothing, gives you 0. That's the same as multiplying these two. So you need both of these to be a 1 in order to get a 1 out here. That's an and that corresponds to multiplying these booleans. Okay, so that's what. So there's actually a dot right there, which isn't a speck of dust, but it's actually me reminding myself that and means multiply, and or is addition here. Okay, so another thing to keep in mind is that these circles mean to reverse the quantity right here. So A looks like you need to negate it. So it turns a 1 into a 0 or a 0 into 1. And you could probably guess that to symbolize that here, you put a bar over the quantity. See how there's all these bars for some of them, not for others. So anytime you need to negate one of these, you put a bar over it. So it looks like not A or not B. So immediately that kind of gives me this, and then we're going to negate that. So then there's bar over that. And then that's combined and with C and D and then negated right there. So it's just kind of a game of, you know, whatever's consistent, you know, just sort of assign a rule and make sure that it's the same rule throughout. And you could probably narrow down a lot of the answer choices just from that, even if you don't know what these symbols mean. Okay, 49. I got that wrong. I don't know much about lasers. I probably shouldn't say anything even about this, but I figured free atoms shouldn't have anything to do with a solid state laser. Those atoms aren't really free. Free electron laser sounded too good to be true. Plus, you know, how are you going to control transition rates for free electrons? It seems like that's not going to actually give you a laser. So I sort of narrowed it down to B and D. Looking back on it, I probably should have chosen D because they're free atoms. So a gas is more like free atoms. And I have no idea what a dye laser is. I incorrectly chose that, but oh well. Chose D. Don't give a theorist an experimental question. All right, 50. Okay, so here we have the energy in the Bohr atom. And I suppose just from doing a bunch of practice problems, having done a lot of these problems in my life, I just know that it had to be proportional to z squared. All right, what happens if you probably did a problem where you had helium with a helium plus with one of the electrons stripped off. It has 4 times the ground state energy. So I knew that there had to be z squared here. And then I wasn't sure right away whether this... So the differences among these C through E have to do with the power of M and the power of E. And so I started to write down what I knew about the Bohr atom, quantized angular momentum. And I was going to use the virial theorem. I was going to say, well, the total energy is proportional to the kinetic energy, just from the virial theorem. So I plugged this in and I figured the velocity might be useful here. So it looks like I took this, plugged in. I forgot about the factor. I didn't care about the factor of 2 because that's not what's distinguishing these. But notice how I wasn't really getting anywhere with this. In particular, this R is going to depend on N. And yeah, I just wasn't getting anywhere with this. But why I eventually settled on C was that I've never seen a formula that had energy proportional to mass squared. It just didn't seem like it would make sense from a dimensional analysis point of view. But it was somewhat of a guess. And I actually there was a question later on in the exam where they they basically gave you a form of this equation, and they were assuming that it was proportional to mass. So I sort of guessed this, and then later on, I think it was question 60 something. Later on, I figured out that was the right guess. Yeah. All right, 51. So 1 and 2 are contradictory. An atom can only absorb specific energies. That's true. That's quantum mechanics. For emission and absorption, they can only do specific energies. They can't emit photons of any wavelength, any energy. So that ruled out 2. And then 3, so 3 is okay. You might wonder why they preface this with at low temperature. They're making sure that you're only counting the ground state and the first excited state. So emission absorption and emission are just between these two, and so that's the same exact frequency. Because once you add more levels right here, then absorption from here and emission don't have to be the same lines, same frequencies, same energies. So they're assuming that it's low enough energy that it's almost all this populated, maybe a little bit of this, and so any transitions are going to be between the two of these. So it makes sense. So after you read all that, it sort of makes sense why they would say at low temperature, and it seems to be okay. So 1 and 3 only. 52. I don't know if it's obvious here, but I actually wrote down d sine theta equals m lambda, and then or I was thinking m lambda, and then smallest angle made me choose m equals 1. It was only after staring at this for 20 or 30 seconds that I realized, oh, this is actually about Bragg diffraction, and there's a factor of 2 there that's important to remember. So if you're doing just general interference, it's d sine theta equals m lambda, but reflection, so for off a crystalline lattice, you need that factor of 2. And then I think, I'm not sure if I just remembered that or if, I think also if you forget the factor of 2, none of the answer choices are there. So then I remembered that the 2 had to be there. But you should probably just remember it correctly right off the bat. Number 53. Okay, so we have 2 different solar systems. They both have the same angular momentum. So because it's a circular motion, so the angular momentum is going to be mRV. So really it's r cross p, and so maybe there could be a sine theta. But if it's a circular orbit, then it's perfectly mRV, and the r's will cancel out. So I'm comparing solar system 1 with solar system 2. So it's mRV equals mRV, and the r's cancel. And they tell us what the ratio of the orbital periods is. So solar system 1 takes 3 times as long. That means it must be moving 1/3 as fast, given that the distances are the same. The circumference of these 2 circles are the same. So this fact and this fact give us the ratio of the masses of the planets. So m1 over m2 looks like it's 3. So the answer was D there. 54. This is a favorite question of teachers, to emphasize that in gravity, all that matters is the mass. So, it's gm1m2 over r squared. If the sun were replaced with a with a black hole of the same mass, the Earth's orbit would be completely unaffected. It would get very cold because we wouldn't get any of the sunlight, but the Earth's motion would remain unchanged. So the orbits would remain unchanged. Yes, we are outside of the Schwarzschild radius, so we are not doomed to collapsing into the black hole. Okay, 55. This has to do with the Doppler shift for light. So this is going to be different than the question a few questions ago with Doppler effect for sound. The Doppler effect for light is square root of 1 minus beta over 1 plus beta, or the plus is up here and the minus is down here. And that has to do with whether whether the light is receding or moving towards, whether the relative motion is towards or away. So it looks like the wavelength has increased, which means the energy has gone down, or the relative motion is away from each other. So velocity of recession. That's why the wavelength goes up, less energy. It's redshifted. So that's why I chose the minus right here and the plus right here. So yeah, that gives the ratio of frequencies of the light. So this is a number less than 1. This is 3/4, which they tell you right here. So the ratio of the wavelengths is this. The ratio of the frequencies or the energies is 3/4, which is what appears generally in this formula. So that's just solving for beta. So yeah, just a little bit of algebra. Let's see how much algebra to actually do here. So 16 plus 9 is 25, and then 7. So you cancel out the 16's, beta is 7 over 25. So you can multiply the numerator and the denominator by 4 to get 28. So again, computation not terrible. Just 3, maybe 4 lines of algebra. Although for 56, the algebra is worse. So again, this is just like problem number 1. This is a relative velocity question. So wind is blowing from west to east. Keep in mind, west is over here. So wind is blowing from west to east. So that means a plane has to head in this direction. So this is the plane with respect to the air, and then the air with respect to the ground. And then we add those two vectors, that's the plane with respect to the ground. So I have in mind the plane with respect to the ground is plane with respect to the air plus air with respect to the ground. So setting up that triangle, I know what to fill in. So how much time is required for the plane to fly due north? We're going to need to know this number in order to solve this problem. So ignore this for a second. The wind speed relative to the ground is 30. And then the plane can fly at 200 kilometers per hour. So I filled in this is 200. This is the plane with respect to the air. So then this is the right triangle, and we need to solve for this. So I know that the answer is going to be a little less than 200. And so I was debating, I think, whether to use the quadratic formula or not. So whatever number this was going to be, the plane needs to fly 500 kilometers. So we have distance is speed times time, this speed right here. And we're solving for time, which is distance is 500 kilometers divided by whatever this is. So it's a number that's a little bit less than 200. So it's a little less than 200 kilometers per hour. So if this was equal to 200, it would take 2.5 hours. So I definitely know that if this is a little bit less than 200, then this is going to be a little bit more than 2.5 hours. And I think I ruled out a couple of them. So I ruled out this because I know it's not exactly 2.5 hours. And this is going to be, so it's going to take a little bit longer than 2.5 hours. This is a little bit shorter than 2.5 hours. So I ruled that one out also. And I guess I could have ruled this one out too for the same reason. I don't know why I didn't scribble that one out. I think I started to notice, so then I couldn't decide between these two. Then I said, okay, maybe I need to actually use the Pythagorean theorem and try and do a little bit of this. So I think I was doing square root of this squared minus this squared, but I was doing a similar triangle, so I just kind of, that's why this is 9 here and this is 400, because I didn't want to write down all those zeros. So I have 400 minus 9 square root of 391, that looked good. So this seemed more like what it was than this, but I think at this point I sort of guessed, and I realized that this would be too much. So this would be 170. So one way to double check that this is not the right answer is that this is saying that this is 170. So 170 squared plus 30 squared is a lot less than 200 squared. So once I started to think about these things, then I chose D without actually solving through all the algebra. 57. Okay, so this has to do with Newton's third law and the contact force between the two blocks. So really, so what's going on here is that in both, stupid pen. So in both of these situations, you have F equals ma. So if you consider the whole object, so the two blocks moving together as a block of mass 3m, you have the net external force is this applied force F, is 3m times a. So you know the acceleration is F over 3m. And then what you can do is you can look at each block individually to figure out what the contact force is. So for figure 1, if I just look at the little lowercase m, what's going on here is, maybe I should draw both of them just to be clear. So if you separate this into two objects, the applied force is being applied to the 2m one, and there's no applied force being applied to this one. But what makes m accelerate to the right is a contact force from the 2m block. So there's a contact force, call it Fc. So 2m is pushing on m to the right. That means m is pushing on 2m to the left with that same magnitude of force, the contact force. And so both of these two objects separately will satisfy sum of all the forces is mass times acceleration. So obviously I'm not drawing the weight and the normal force for each of these. So this one's easier. The contact force, sum of all the forces, is its mass times its acceleration, which is the same as this acceleration, F over 3m. So m's cancel out. Looks like the contact force is F over 3 for figure 1. And then a similar kind of analysis, but applied to the 2m block, says that the contact force for this case is actually 2/3 of the force. So yeah, being comfortable with Newton's third law will get you to B right away. 58. If we look at just block B, a free body diagram, a free body diagram for just block B, the only thing pushing block B to the right is the frictional force, the static frictional force. Okay, so there's a static frictional force there. And we're given the acceleration. So the net force on block B, so again, there's a mg pointing down and normal force pointing up, but the net force is equal to the static frictional force. This is the mass of block B times its acceleration. So the mass of block B is 10 kilograms. They give us the acceleration is 2 meters per second squared to the right. So that means that this force, the force required to get that acceleration, is 20 newtons. So, okay. Hey. 59. I got this wrong because I didn't read the question carefully enough. I just thought they were talking about must have been pretty sick of the exam by this point. So I just figured it was a pendulum, and I totally ignored the fact that it was in an elevator. I just said, oh, pendulum, this is the frequency, this is the period. But no, if the pendulum is in an elevator that's accelerating upward with constant acceleration a, effectively that's like being in a gravitational field that's stronger. So instead of G, it's like a gravitational field where G is replaced with G plus A. So if the acceleration's 0, then we're not modifying this formula. If the acceleration is equal to G upwards, you're really going to feel that a lot. So this equation looks very similar, except the period, instead of looking like this, is going to be 2 pi, this one right here. All right, 60. Okay, so we want the magnetic field as a function of x here. So first of all, the direction. So the magnetic field here is a sum of 3 pieces due to the 3 wires. And for each of these 3 wires, has a magnetic field contribution here that points out of the page, so towards us. Just by taking, take your right hand and wrap it around this wire so that your thumb's pointing in this direction. Your fingers are pointing out of the page right here. So that direction out of the page is the positive y direction, right? X cross out of the page gives you, if you curl your fingers of your right hand, you get your thumb pointing to the right. So the answer should be y hat, at least for positive x. It should point in the positive y hat direction. So that let me get rid of answer choices A and D right away. So to distinguish among those three, I figured, well, maybe I actually have to do a little bit of math here. So if this is x, if x is this distance, I wanted to figure out the distance to this wire, which is equal to the distance to this wire, just from symmetry. So I know the distance to this one. So I'm kind of getting, once I write this down, I figure out that, this, so this angle is 45 degrees, meaning this angle is 45 degrees. That gives me this length right here. And I'm starting to see, oh, well, this has two contributions from these two. This distance is off by a factor of square root of 2 from this distance. So there's no way for a number plus 1 over square root of 2, or any number over the square root of 2 times that number, to nicely combine. So I'm starting to lean towards this one. But I still go ahead and do it. So I remember that from Ampere's law, integral of B dl is mu naught I enclosed. And so the magnetic field due to an infinite wire, well, this is 2 pi r, which moves over here. So I have mu naught I over 2 pi r for each wire. So this is due to the central wire right here. That distance is just x. This factor 2 has to do with the 2 other wires. Both of these have an equal contribution. And then 2 over this distance, which is 1 over square root of 2x. And that's exactly what this one is right here.